Now the question is asking us to find out how many of the following are polar. Now to do this, we're going to have to look at the partial charges, which will help us find the bond dipoles, and then the molecular geometry to figure out if the dipoles cancel and if there's a net dipole. Now it's going to be polar if there's a net dipole, and it's going to be nonpolar if there is no net dipole. Now first we're going to start off with this one right here. We have both F's bonding to the O's, and we have 20 total valence electrons, and we give F an octet and the other fluorine an octet, and we add the four remaining here as lone pairs. Now to draw the molecular, first we have to find out which one is more electronegative, and we know that it's fluorine, so we draw this right here and this right here, and then we draw the partial charge above the oxygen. Now we have to draw the bond dipoles, which point towards the more electronegative element. So that's fluorine, and then we draw the other one right here going to the other fluorine. Now we need to draw the molecular geometry. We have oxygen right here, and we have a lone pair right here, and a lone pair right here, and then we have fluorine and fluorine, and we draw this bond dipole and this bond dipole. Now we see we have bent molecular geometry, and we find out that there actually is a net dipole, so we know that this has to be polar. So we can put a check next to here to say that it's polar. Now we have our next molecule, and we have 3 O's bonding to the S with double bonds, and we have to have a total of 24 valence electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's a check with all the valence electrons. And we know that oxygen is more electronegative than sulfur, so we draw the partial charges above all the oxygens and the partial positive right here. So we draw our bond dipoles right here. Now we need to draw the molecular geometry. We have our sulfur in the middle, and we have our oxygens right here. We know that it's trigonal planar geometry because of the 3 bonding domains. And now we draw our bond dipoles right here. All angles are 120 degrees apart. And the rule is that in trigonal planar, if all domains are the same, then they all cancel. So it's nonpolar because we all have 3 single sulfur oxygen bonds. Now for our next one, we have to actually draw the Lewis structure, and we know that there are 7 valence electrons from chlorine, and since we have 2 chlorines, we multiply that times 2 plus the 2 that we get from beryllium, and that is a total of 16. So first we make an octet on this chlorine right here, and next we try and fill an octet on this one right here. And we see that we already have a total of 16, so we're good. And we draw our partial charges, and we know that chlorine is more electronegative than beryllium. And now we must draw our bond dipoles right here. And now we must draw the molecular geometry. And once again, the bond dipoles. And we know that it's linear and that the bond dipoles cancel out, so that means it's non-polar. Now for the next one, we have 32 valence electrons and we have to see if we have all the electrons. So we have 8 right here, 8 right here, 8 right here, and 8 right here. So that makes 32. So check for the valence electrons. Now we have to put the partial charges. We know that chlorine is more electronegative than carbon. So we draw the partial charges. And next, the bond dipoles. And now we must draw the molecular geometry. And since we know that there's 4 bonding domains, it's tetrahedral. And now we draw the bond dipoles. And for a tetrahedral molecular geometry to be nonpolar or polar, for it to be nonpolar, all the net dipoles have to cancel out. And since we know we have 4 carbon-chlorine bonds that are all the same, that means everything all the net dipoles or bond dipoles cancel out, and we have nonpolar. Now in the final one, we have ozone, which has a total of 18 valence electrons. Now, for this molecule, we have to have resonance structures, and we have the choice of putting the double bond between these 2 oxygens or these 2 oxygens. But regardless, we still fill up with 18 valence electrons. And we can draw the molecular geometry right here, with our lone pairs right here and our other oxygens right here. We don't even need to draw the bond dipoles because we already know that it's going to be polar because all the bond dipoles aren't the same because one of the bonds is not even a bond, it's a lone pair. So we already know that that is going to be polar. Now, out of all of these, we have 2 polar molecules. We have this one, and we have this one. Now, a common mistake that people would make is that they would not even know how to draw the Lewis structures, and they would get all of these wrong, which would make the whole problem wrong. Or, for this one, they would confuse this and make this count as an actual bond dipole, and they would say that this is nonpolar, and they all cancel out.